Good morning, everyone. This is Mr. Ranger with you. We're going to get into lesson 4.8 here in AP Pre-Calc and go over three different types of regression from linear to quadratic to exponential and compare their residual plots to determine if which model of the three is a better fit to the data. All right, and it's a big lesson here, and there's a lot to talk about, so let's get started. Okay, so while eating out has many fun perks, all right, there are also associated costs to consider. Is it true that eating out is always more expensive than cooking the same meal at home? Well, we're going to talk about that a little bit. If so, has that always been the case? Today we're going to look at the ratio, okay, the ratio of restaurant to grocery store prices for the same meal over time. Okay, so the ratio that we're talking about here is the restaurant to grocery store. So restaurant price, okay, restaurant price, okay, compared to the grocery store price. So, what you have to pay going to the grocery store to make the same meal. Grocery store price, okay? And we're going to look at that over time. A ratio is a comparison of two things. That's all a ratio is. So we're going to take a look at that and see what's going on from 1960 all the way to 2014. So we're going to take a look at the data here, which is off to the right. You have that into your window. You have the lesson to the left, and in the middle you have the data set. And I screenshotted a bunch of the graphs for you, so it'll make it easy to discuss. We'll incorporate decimals as well. And then you have the homework off to the right, which obviously you need to do after we're done here. And notice that the data set here starts off at 1960, where x is equal to 0. And we're not going to be using the 4 digits for the year just to make it a little bit easier to enter in decimals, because otherwise there'd be a lot of data to put in decimals here. And the restaurant to grocery store retail price ratio. Again, this is a ratio, so let's write it down one more time so we understand what these numbers mean. Because again, numbers are meaningless without understanding how they're generated. So what they did was they took the restaurant meal price, okay, restaurant meal price, and they divided it by what it would cost to go to the grocery store to produce the same thing or to produce the same meal. So grocery store, all right, price. And what they did is they recorded that from 1960, where x is equal to 0, all the way to 2000, I think 14. We'll take a look at that. So when x equals 0, we're going to represent that as 1960. So this is our initial starting year. And then when x is equal to 1, that means 1 year past 1960, which is 1961. So the value of 1 represents 1961. The value of 2 for x represents 1962. The value of 3 for x represents 1963, and so on. All the way, if you go down, all the way down to the data set, when x is 54, all right, we're talking about the year 2014, which hopefully makes sense. So this is equal to 1960 plus 54, which obviously is equal to 2014. Okay, so we're not using, the input value is not a 4-digit number for the year. The input value is either a single or double digit representing the year. And as you can tell here, if you take a look at the ratios, again, these are ratios, restaurant meal price to grocery store price, purchasing the same, let's say, ingredients to make that meal in a restaurant. And it starts off at about 1.4, which is about 1.4 times as big. So the restaurant in 1960, to get a meal in a restaurant, it was 1.4 times as expensive as the grocery store price. Okay, so it's a little less than 1.5 times is more expensive, which to be expected. Typically, restaurants, in order to stay in business, they have to upcharge everything they do or everything they sell in order to make money. Okay, and let's go back to the questions here, just so we can take a look at them. It says, looking at the data, look at the data, showing the restaurant to grocery store price ratio. All right, in the years since 1960, to 2014. What do you notice? What do you wonder? Okay, so let's talk about that for a minute. So if you look at the ratios here, all right, they're all greater than 1. Okay, if these two meal prices were the same, the ratio would be 1. All right, but they're not 1, which means the restaurant meal price is greater than the grocery store price. And so that's the first thing I notice. And notice that also if you look at it as the year goes on, as time goes on, the ratio increases all the way up to 2014. You're talking about a ratio of 3.8, almost 4 times as expensive to eat out at a restaurant than it is at home, shopping by yourself, going to the grocery store. Okay, so first of all, we notice a few things. So first, all right, first, all the ratios are greater than 1. All ratios are greater than 1. Greater than 1. Okay, and that means that the restaurant meal price is greater than the grocery store price. That's what that means. So restaurant price is greater than the grocery store price. Just abbreviating here to make it quick and easy, okay? That's what it means. If they were both equal and you divide two equal things, we'd get exactly 1, but they're not equal. Restaurants typically charge for a meal more than what it would cost to produce it by going shopping by yourself, okay? That's typical. Okay, secondly, the restaurant prices, okay, are increasing over. That's what it means. All right, if they're all greater, the ratios are all greater than 1, and it's increasing over time, that means that the restaurant prices are increasing over time. So restaurant prices are increasing over time. And I know that we're in the year 2025 right now, and I can tell you that going out, eating out today is so costly and so much more expensive than it used to be, even just, 10 years ago. Okay, so they're increasing over time. Okay, and then also the thing that I don't know about in this example is that it says restaurant. So does this include fast food? I don't know. Does restaurant, is that a general term that includes any business, okay, that is selling food, like Jack in the Box, for example, or In and Out? I don't know. So and I'm answering the last question here, what do you wonder? Is fast food uh, incorporated or included in this data? Question. Okay, I don't know. Okay, now it says go to Staplet.com and click on the two quantities variable. I'm not using this right here. We're using Desmos through here. So in this section here, I'm going to give you the Desmos link, and it's in our Canvas and our website. So we're use Desmos, all right, and we're going to use the link in Canvas. So if you're watching this video at home, pause the video if you haven't done this already. Get the link and open it up, and you're going to see the data, all this data right through here in Canvas. Oh, and I also included the data link so you can see it right through here. So just make a little note, go into Canvas, okay, and use the Desmos hyperlink. I don't think this is the right one. I'm not sure. It might be. I think so. But go into Canvas and use Desmos hyperlink just to make sure. Okay, because I update things from year to year. Okay, this is the third year I've been teaching the course. Okay, let's go back here. It says, what is the explanatory variable? What is response variable? Okay, so what does that mean? So the dependent variable is called the explanatory variable. Okay, so just in here, let's make a little note just to, especially if you guys take stats later on, they use different jargon for similar things. So usually the input value x here, this is your input, is the x values right through here, x equals 0, 1, 2, and 3, and so on. Okay, that is That is called the independent variable, okay, or the explanatory variable. So the independent variable typically is x here. Oops, I didn't mean to variable r. Okay, variable. That is your input, and typically is x, but in stats, okay, they call that the explanatory variable. Just so that you guys know some jargon. Explanatory variable, okay? And your dependent variable, typically the output, so dependent variable, come on, Ainsworth, there you go. The dependent variable, which is your output variable, and that's typically y, is called the response variable, which kind of makes sense. It depends on the input, right? So it's called the response variable. Okay, that's if you use if you actually do go to stabler.com and then use this, enter the data and use these sort of things, which you can do instead of using Desmos. Just make sure you know which is which. Okay. All right. And then number 3. Okay, look at the scatter plot. Describe how the restaurant or grocery retail price is changing over time, and then sketch below. Well, I put the screenshots of the graph in your lesson here to make it a little bit uh, more user friendly right through here. So let's take a look at it. Okay, let's graph this data set, and then again, this data set here is in Desmos. So let's go to Desmos here and click on the link in Canvas, and boom, this appears. Okay, and this right here is the data set. So and there's a lot going on here, so I'll explain it a little bit at a time. So our first column here, our x values, if you look at the table, are from 0 to 54, corresponding to the years 1960 to 2014. Then I've got the predicted values y1 in the second column, and then e1, e2, and e3 are called the residuals. Okay, now the residual is the actual value minus the predicted value. Okay, and those are automatically calculated in the spreadsheet. The red line here is your linear regression line, y1, tilde. Okay, that's how you enter in a regression line, is using the tilde and not the equal sign. mx1 plus b, where x1 is your input, and then y1 is your predicted value or your output. And then notice on the graph here, they show you the linear regression line, they show you the data set in purple and the residuals in green. Okay, it's all color coded. So the red line is your regression line, called the least squares line or the linear regression line, or simply a trend line that you guys learned starting in hopefully middle school. And your data set, the actual values that are given, the ratios, are in purple. And those green dots that you see, those are the residuals that are found by taking the actual value in the data set minus the predicted. Okay, and so this graph right here, I screenshotted and I brought it into your lesson, and so we can talk about it, obviously. Okay, so let's see here. It says, describe how the restaurant grocery to retail price ratio is changing over time. Okay, so let's go ahead and do that. So notice, let's zoom in here a little bit. Notice that we have a trend going on. It's definitely increasing over time. So from here to here, right about, I would say, right about here. And this is, if you zoom in here, that's about, x equals 28. So I'm obviously rounding here. X equals 28. And 28 past 1960. Well, let me see, that's 1988. So at 1988 there, 1988, something changes. So it's increasing here. It's gradually increasing here. I'm going to write that down. It's gradually increasing. All right, but then something happens after 1988. I mean, look what happens. Okay, it increases rapidly, or it increases more quickly here. So increases more quickly, you can say more rapidly, however you want to say it. So something changes, in 1988. And that, my friends, is the answer to the question. What do I notice? Well, it's generally increasing, but at that moment in time in 1988, then it increases more quickly. So let's make a little note of that. All right. So the ratio, again, this is a ratio now. Okay, the ratio increases. Okay, over time. The ratio increases. Oh, come on, I gotta spell that correctly here. Increases over time, and more rapidly after 1988, because that's for some reason something happened in that year, all right, and it increased more rapidly. Okay, and that's just, again, you're describing, right? You're describing what's going on. It definitely increases over time, but more specifically, after 1988, something happens. Not sure exactly what that happens, but it increases more rapidly after that point. Now, number four, it says, suppose we want to find the equation that would help us model the data, uh, model the price ratio, okay, model the price ratio based upon the number of years since 1960. And this is important right here. So let's highlight this. You have to know how to what to enter in the data or what the data set is when you model it, whether you use Desmos or some kind of uh, stat software, okay, statistics software. You have to know what data to put in there. And it says we want to model the price ratio, but it's based upon, all right, the number of years since 1960. And that's why x starts at 0 here. So x equals 0. All right, that represents 1960. And then 54 years later, when x is equal to 54, that's 2014. So right here, the number of years since 1960 means that we start, okay, at x equals 0 and then go on from there. The least squares regression line, all right, the least squares regression line fits the line to the data. All right, now least squares is a fancy name for the linear regression line. Okay, this is called a linear. This is what you heard probably in grade school, a linear regression line, and in not grade school but middle school, and they probably called it a trend line. Okay, very common topic taught when you're dealing with linear functions because we're talking about a line. And so just remember this fancy name, least squares regression line, is just a trend line. It's a linear trend line. Okay, and now when you do that and when you enter the regression line in Desmos, okay, and this is a Desmos command, not other software here. You have to enter it as following here. So you go y hat, okay, that's the predicted value. Is not equal to, sorry, is tilde. Go tilde. This is a special symbol that is used for your regression model. All right, is equal or tilde approximately equal to, excuse me, I'm sorry, y1 hat. Got to use subscripts because the data, if you look at the data set right here, notice the data set, it's our first table, so it references x1. And notice that our y values are not just y, it's y1. Okay, so you have to use subscripts here when you enter this in. So y1 tilde is m times x1, all right, plus b. And there's your linear, what's called a linear regression line or least squares regression line. Okay, where the hat symbol is called your predicted value. So y hat, like this right here, is predicted value. Again, there's, like I said, there's a lot going on in this lesson. Once you get through it, it's actually pretty straightforward, but if this is all new to you, well, it's not pretty straightforward. Now, what is that? Okay, so we're going to go into Desmos here, and let's do that. We're going to switch programs. So notice that I already entered it in for you, just to make things easier. So if you turn off the colors, you just see the data set and the residuals, and then if you turn on your what's called your least squares regression line or your trend line, you can see how it runs through the data set, but not very well. This is not a good approximator, and if you've ever learned anything about regression, the regression line, if it models the data well, will do two things. Number one, it'll go through the data set, which this doesn't really do, okay, because the data set's non-linear. And second of all, the residual plot will not have a pattern. Like this green residual plot here kind of looks like it's U-shaped. It's got a pattern to it, and that is a giveaway that the trend line the regression line that you made in this case it's a linear regression line, is really not a great model of the data. All right, so let's go back here and take a look at it. So here we go. Now M stands for slope. So if you take a look at here, M is the slope, as you guys know, in slope-intercept form. This is slope-intercept form that you guys are familiar with in Algebra 1. And as I'm sure you know, M is the slope, and then B is called your y-intercept. And since we know that the program here, Desmos in this case, it gives you both. So writing the equation is easy. It's going to be y is equal to 0.0414481 times x plus 1.07348. Okay, you just substitute those values in there and write the equation. All right, so let's write down what I just said here. So we have for our regression line here, and we're going to put a little hat symbol on there because it's a prediction, okay, is equal to 0.04144, right, 81 times x, right, again, this is slope-intercept form, plus the y-intercept of 1.07348, all right. This is what's called your regression line, your trend line. And it's found by just looking at the values here. So just double checking right now. The slope is 0.0414481. Good. The y-intercept 1.07348. Very good. And this is what we could use to predict the price ratio, all right, given any year we want. It says, what does this model assume about how the price changes each year? It changes each year. What is the model? Well, this is a linear model, right? And because it's linear, we know that it has a constant rate of change. So linear means that there is a constant rate of change, ROC, which you've seen basically every day all year long. Rate of change, constant rate of change of the price ratio. Which is really not the case. If you take a look at the data here, and you go all the way over here and take a look at the rate of change over here, it's not constant. Okay, so it says, do you think this is a good model? Well, a couple of reasons that I think no. So no, number one, the data is not linear. So number one, data is not linear. And number two, if you look at the residual plot here, the residual plot is not supposed to have a pattern. It's not supposed to, look like a parabola, for example. Like this residual plot is parabolic. And because of that, the model is not a good one here. So residual plot shows a pattern, and that tells us the model is no good. Model is not, okay, a good one. Okay, so if you look at the residual plot here in number 5, which I provided, I just took a little screenshot of the residual plot and just isolated it here. You'll see that if the residual plot follows this parabolic pattern. Okay, it's parabolic. So parabolic, that just means parabola-like. Okay, parabolic pattern. And that tells me that the model is not good. Now, I knew that in the very beginning because if you just look at the data set again, go back to the original data set, the line where the data is not lined up in a linear fashion, okay, the line does not go through the data very well at all. So that's the first cue. And then not only that, the residual graph, when it has a parabolic or some type of pattern, whether it's concave up or concave down, it doesn't matter. You know the model's not good, okay? So here, I'm going to make a note again just to make my point here. So it's a parabolic pattern, and that tells you that the linear model is not good. Linear model, okay, is not good. Okay, that means we're going to have to go look at another model. That's why we need to explore quadratic and exponential other models to see if it fits the data. Okay. All right. Let me see. Number 5, a residual plot shows the difference, keyword difference, between the actual and predicted value by the regression model. Okay, provide a sketch. We already provided it for you. And then what we should do though is actually show you. Okay, so let's actually calculate the residual using some values just so you can see what I'm talking about. Because this is like an important, this is the first major key concept here. So I'm going to write it big, bold, and red. So it says here the residual is the difference between the actual and the predicted value. So let's write it down. Let's put it in red. Okay. So the value, residual value is equal to the actual value minus, all right, minus the predicted value. Now, I included a definition up here at the top, and you can read it at your leisure here, that describes exactly what the residual means, graphically. It's the distance either above or below the trend line, but it's really the difference between the two, the difference right here between the actual and the predicted value. You simply subtract, okay? And if it's positive, it means one thing. If it's negative, it means another thing. We're talking about over and under estimates depending on whether it's positive or negative. Okay, so let me give you a little example here. So go back to number 5 and let's calculate the residual. Now the Desmos does it for you, but I want to show you how this residual is calculated. So it says the residual is 0.36852. Just look at that graph right here. Okay, just get focused in on this here. So let's take the actual value, which is in purple, 1.442, subtract your predicted value, which is given by the trend line, which is 1.07348. And if you subtract them, which we want to do here, okay. Let me get my lesson back here. There's just go on, do a little split screen stuff here. Give me a second. There we go. All right, there we go. All right, so let's go down here and let's just do a simple calculation, 1.442. Again, I'm just showing you this to make it concrete, minus the predicted value, 1.07. All right, 348. You'll notice you get 0.36852, all right, which is our predicted value or our residual value on the graph. All right, we can see that. So the residual value, you simply take your actual value in the data set. Okay, again, this is from the data set here. Subtracted the value, predicted value, and this is where you use the equation, use your model. Okay, and you subtract the two and you get your residual. And notice that it's a positive number. And the reason why it's positive is because the actual is bigger than the predicted. Actual is bigger or higher than the predicted value, which means that we have an underestimate here. So this is called an underestimate. So positive residual means underestimate, negative residual means overestimate. Okay? Okay. All right. What else? Let's get back to it here. Probably didn't need to go to full screen, or split screen, but that's okay. It says, in which years does the regression model give an underestimate of the true ratio? Well, let's go to the graph. Okay, so here's the graph here. Now, if you take a look closely here, we're looking at an underestimate. So in which years does the regression model give an underestimate where the predicted is lower than the actual? Okay, so we're talking about underestimate here. So right about here, there we go. So what year is that? That's around, let me see, that's around the 12th year. Close around there. Oh, I missed it. Let me change my line here. Sorry. Right through here. There we go. All right, and that's when x equals 12. And then over here, here we go. Let's go ahead and just go down to the x-axis so we can read it through here. Let's zoom in here so we can take a look at it. So here, this is at x equals 12. 12, and this is 1960 at x equals 0. 12 years after 1960 is 1972. So from 1960 to 1972, we have an underestimate. Because the predicted value is less than the data set, or less than the data values. And then here, this is about at x equals 45, about 45 and 1960 plus 1960. That sounds like 2005 to me. And that's where things change right there. So from 2005 on, okay, we have an underestimate as well because the predicted value is less than the actual. So this is also an underestimate. Okay, simply meaning that the trend line is lower than the actual data, which means the predicted value is going to be less than the data value. And so in between here, so in between these years, we have an overestimate because the line is the predicted value. Again, this is the predicted value in red, okay, given the trend line here. And notice it's higher than the data set, okay, so keep that in mind. So this is your data, actual values. Let me write down actual values here. So actual values are in purple. It's from the data. All right, through here. So in between 1972 and 2005, we have an overestimate, right? The predicted value is higher than the actual, so we call that an overestimate. Okay, so let's just jot that over here. Okay, so from x equals 0, which is 1960, to x equals 12, which is 1972. All right, we have an underestimate right there. Okay, and from, let's say, from x equals 45 on, so from 2005 onward, if I could spell here, so onward here, we have an underestimate. Okay, in between those two times, we have an overestimate. So an overestimate from 1972 to 2005, roughly. And there we go. Now, as I said earlier here, number 8, what would you expect from the residual plot for the regression model to be a good fit? So good fit here. So no pattern. You do not want to see a pattern in the residual plot. So if the model is good fit, so if the model, whatever type it may be, if the model is a good fit, and you're going to see this here in a minute because we're going to change models, good fit, you do not want to see a pattern in the residual plot. Okay, no pattern should exist, all right, in the residual plot. Okay, and that's going back to what we just said here. We did see a pattern here. It's parabolic, okay, in the residual plot. So look at the one in green right through here. Whether it's concave up or down doesn't matter, okay, but if you see a pattern in the residual plot, it means that the model is no good and you got to switch models, which is what we're going to do right now, okay? We're going to switch models here. So let's go back to number 9. So perhaps a linear model is not the right fit, okay? It's no good, as we've been talking about. Calculate other regression models. So this is going back to that stat program, which we're not using. I'm using Desmos that I provided for you guys right here. So we're going to be using that. And what we want to do is take a look at the quadratic and the exponential models to see which one would be better. All right, so it says describe what a quadratic model indicates about, well, I'll answer that here in a minute. Let's go to the quadratic model. So let's open up Desmos again. Okay, so I gave you guys the link here. Okay, and so what we want to do is turn off E1. So don't delete anything, just turn off the color. Follow me. And I'm showing you guys how to use Desmos here. Turn off the color for Y1. And what you want to do, or for the linear regression line, and notice that the data set still appears, okay? So no problem there. And turn on your quadratic model. So just hit the color. And you'll notice that the quadratic model, ooh, it's much better. It goes through the data set pretty well. The question is which one's better? Is the quadratic model better than the exponential, or is the exponential better than the quadratic? I don't know. Just turn it on and we'll see. Okay, and you can see there in blue is the exponential, a times b to the x power. That's your exponential. And notice it doesn't do a good job like the orange one does, which is the quadratic model. So already, just by looking at it, I can see that the quadratic model is better. Not only that, the r squared value is 0.99, is extremely close to 1. That's an indicator that it's a better model. And notice that the r squared value for the exponential is only 0.96, which is not as close to 1 as 0.99. So this tells you, the r squared value tells you if it's really, really close to 1, how good it is to represent or model the data set. Okay, so I can see here, I'm going to turn off the exponential one there. And so look at only the quadratic, the second degree function. Look how good that is. And what we want to do is turn on the residuals. So turn on E1, and those are the residuals for that. Look at that. There's no pattern in the residual graph. I'm talking about the points above and below the x-axis right there. But if you turn that off, so let's turn both of these off and turn on E3 and the exponential one, and you're going to see something here. Look at this. So the blue function here is the exponential regression function, okay? And notice there's a pattern in the residuals. It's parabolic again. It's U-shaped, okay? And because of that, it tells you that the exponential function is not a good model either. Now, I did something nice for you guys. I go ahead and I screenshotted all this stuff so you have it in your lesson. So let's go back to the lesson and let's take a look at it. Okay, so all of these screenshots were from Desmos, okay, and then I just brought it into my lesson here. So the quadratic model, y1 tilde, mx1 squared now, there's your quadratic model, plus b1 plus c, okay? Notice that r squared is very close to 1, which represents this right here. If you take a look at it, this is close to 1, right? Close to 1, which means it's a good model, okay? It's a good model. Not only that, there's no pattern in the residual plot. No pattern. You know, I should have put this in orange just for color coordinated. So no pattern. That tells me that the model is good. Model is a good fit, okay? Good fit for the data. All right, where if you take a look at it, you compare the exponential one, look down here, let's look closely here. The residual plot has a pattern, it's parabolic, and that tells me something, that the residual plot has a pattern. And that tells me that the model is not good, is not a good fit for the data. So the exponential model is not, okay, a good fit for the data. All right, and that tells me. So that's a really, really important thing, and it's one of the key ideas in this lesson that you need to take out with you is that given any regression model, whether it's linear, quadratic, or exponential, you look at the residual plot, and if it has a pattern, you're gonna it indicates that it's not a good model, and you're gonna switch models. Okay. Now the quadratic was better, but let's go ahead and write the models down so we can see them here. Okay, and it says describe over here, part A, 9A. Describe what quadratic model indicates about how the restaurant to grocery store ratio, all right, is changing over time. And you guys know something about quadratics here. So quadratics, the rate of change, here, ROC, the rate of change of the rate of change is constant. That's what it implies, but that's really not what's going on in reality. Okay, in class, we used to refer to this as the second difference is constant. The second difference is constant. All right, now it says write an equation. So what we're going to do is take the values right here. Okay, all you do is just sub them in right through there and write the equation. Okay, and that's a lot of digits. So here we go. Okay, so the quadratic equation here. So y hat, all right, y hat is equal to, you use the equal sign when you write the equation, a 0.01, let's see here, 0.00109, 0.00109, all right, and then 738, geez, there's a lot of digits here, 738 times x squared, and then b is negative 0.017, so minus 0.017, 8103 times x, and then c is positive, so plus 1.59693. And there's your quadratic equation, second degree prediction. And remember, this is called the predicted value. If we use this equation, we get a predicted value from the model. Okay, it's called a quadratic model, regression model. And you input the year in, and it spits out the predicted ratio for that year. That's what it's used for. And then the exponential model, what is it? Indicates how the restaurant to grocery store ratios change. How is it changing over time? Well, we know about exponential function. So this one here, all right, the restaurant to grocery store ratio. So the restaurant, all right, to grocery store ratio, all right, is changing, is changing, sorry, all right, by what's called a constant proportion, by a constant proportion. Let me refresh your memory on what that means. So by a constant proportion, which means, okay, that there's a common ratio. Common ratio from year to year over time. That means in terms of terms here, A2, R is equal to A2 divided by A1, or you take A3 divided by A2. In our example, it's from year to year, so maybe 1961, all right, to 1960 is going to be equal to 1962 to 1961. Okay, so from year to year, you take any two consecutive years, and the ratios will be the same, which means they have to be in same proportion, constant proportion. All right, and it says write an equation for the regression model. So here we go, let's do it. So again, this is the predicted value. When you see that symbol, that y hat, it's called a predicted value using the model. And if you look down here, right here, we just have to take these values here and substitute them in. So the base is 1.28539. Excuse me, the initial term, sorry. And then the base is 1.01821. So let's write that down up here so we can see it. So here, 1.28539 1.285, maybe forgot the values, 1.28539 times the base, which is 1.018. Hard to remember all these signs. 21. Okay, 21 raised to the x power. Okay, and there's your exponential regression model for this data set. And then it says looking at both residual plots. All right, here, which function do you think is better? We talked about that already. Okay, so quadratic model is better. Because the residual plot has no pattern. So let's put that in. Because the residual plot has no pattern. Okay, the exponential one does. And it says use your chosen model, okay, which is this one, all right, to predict the restaurant to grocery store retail price ratio. So predict the price ratio for 2023. So what year is that? Well, it's 2000. I mean, what X value is that? Now, so it's the number of years past 1960, right? So we have to understand that, we have to think, how many years past 1960. So that's 63 years, right? Past 1960. That's in the beginning of the data set. So what we need to do is find that value. So here we go. Our predicted value would be approximately equal to point. Let's go look up top here using our quadratic function here, which is this one. Holy cow. We have to type this in. So 0.001.0010978 times 63 squared minus 0.016. Look at the top of the screen, guys. And then 0.018103 times 63, and then plus 1.59693. We got to enter this in the calculator. So let's go back to the Desmos and let's do it the easy way. All right, so we have our function here. Oh, no, we have to type it in. Damn it. Okay, so, well, you know what? Okay, I'll show you something. Watch this. I'm going to type in the function. So looking at this one right here, let's bring this one down here. I'm going to type the function in. I'll show you something cool. So y is equal to, and again, I'm going to type the function that we just wrote down in. But I'm looking at the decimals right here. So 0.00109, right? 738 times x squared. I'm writing the equation now. So minus 1, nope, 0.017813. That's the linear coefficient, so times x, and then plus the c value. So plus 1.59693. So there's the equation, and then I convert it to a table. Watch this. I'm going to convert it to a table, and then I'm going to put the value that I need in there, which is 63. I want to go 63 years past 1960, which is 2023. So you type in 63, and then it outputs the value. So we predict the ratio to be about 4.83. Oh, how cool is that? Click save. All right, so that's how you do it. That's one way to do it there in Desmos. So what did I just say? So it was about 4. Oh, let's look. 4.83. All right, there we go. So 4.83. That's a ratio now. And again, this is equal to the restaurant, okay, restaurant price to grocery price ratio, which means restaurant price is about 4.83 times that of the grocery store price. So this is what it means here. So the restaurant meal price is equal to 4.83 times the grocery store meal price, which is almost 5 times more expensive. in 2023. And I know for a fact that things are going up over time. And when, because I'm obviously a father here, and I pay the bills when we go out, as long as went along my wife here, and we have seen the prices of restaurants for just basic meals just escalate. I mean, I just went to Mad Madeline's, for example, and the Monster Burger was $30. I mean, when in history has a single burger, be $30? I mean, that's ridiculous. Granted, it's the Monster Burger double patty, but give me a break. Paying $30 for a hamburger at a fast food place, even Mad Madeline's, that's like ridiculously high. Okay, so there we go. That was a lot. Now there's part two of the video, and part two of the video continues here. I'm going to stop the video here because part two covers the learning targets, and it also covers the check for understanding. All right. And again, this is a video. Hopefully it helped you out. And there's a lot involved, and hopefully you learned something, okay, about regression lines, about the residuals, and about how to tell if a model, whether it's linear, quadratic, or exponential, is a good fit for the data by using the residual plot. All right. This is Mr. Ainsworth here. Hopefully I'll see you in class. You guys take care. Bye-bye.